So last time around, we looked to see how induction can be used not just as a proof technique, but also as a technique for constructing programs. And we illustrated this by means of an example. We saw how the idea of so-called constructive induction could be used to obtain a fast version of the standard function which reverses a list. So what we're going to do today is we're going to kick things off with a quick review of what we did last time around, and then we're going to be doing two things. First of all, we're going to be doing a second example of constructive induction. We'll be seeing how it can be used to obtain a fast version of a function which flattens a tree. And then secondly, we're going to be looking at the final case study which we're going to have in the course, which is a compiler correctness result. So here is a quick summary of what we achieved in the last lecture. So what we have in the top red box is the standard recursive definition for the reverse function in Haskell. And I've abbreviated it here by rev rather than reverse, just so that everything fits more cleanly on the slide. And then what we have in the red box at the bottom of the slide is the faster version, which we obtained by using the process of constructive induction. So we can quickly just talk about these two red boxes again. So at the top, we have the standard recursive definition for the reverse function. And the important thing from our point of view is that it's defined in terms of the append operator for lists. And what we found with the append operator in the last lecture is that it takes linear time in the length of its first parameter. So append takes two lists, it takes linear time in the length of the first of those two lists. And then when we went further in the last lecture, we found that when you use the append operator recursively in the definition of the reverse function, like this, then this means that the reverse function actually takes quadratic time in the length of its input list. So the summary here is that this is a slow version of the reverse function, and you see a sad face here. So what we saw then in the last lecture is how you can obtain the faster version of reverse in the lower red box. And the trick that was used is that it's defined in terms of an auxiliary function, rev prime, and what rev prime does is it takes an extra list as a parameter. And this extra list is going to be used to accumulate the reverse of the input list. So as I've highlighted here in yellow, initially the accumulator is going to be empty, and then as the reverse prime function progresses, it's going to successively take the first value in the input list, and it's going to put that onto the accumulator on the right hand side. And what we find when you look at the time complexity of this function, this one turns out to be linear time complexity. So it's a faster version of the reverse function, sometimes called fast reverse, and we see we have a nice smiley face. And the interesting thing is how we actually obtained this two-line definition for reverse prime. What we did is we specified the desired behavior of the reverse prime function using an equational property. And then we used that equational property together with the process of constructive induction to actually calculate in an entirely systematic manner the two-line recursive definition for the reverse prime function. So we didn't need to know this definition in advance. We essentially got it for free from the equational property which characterizes what reverse prime has to do by applying the process of constructive induction. So to just summarize again, at the top of the slide we have slow reverse, which takes quadratic time, and at the bottom of the slide, using the process of constructive induction, we came up with, in an entirely principled and systematic manner, with a fast version of reverse which now takes linear time. The first of the new things that we're going to be looking at today is a second example of constructive induction. So the example we're going to be looking at is how to implement an efficient function that flattens a tree. So we'll start things off by defining or declaring a data type for simple trees. And I'm going to make this a particularly simple data type. I'm not going to have any parameterization involved. And I'm going to have two constructors in my tree. I'm going to have a leaf constructor, which takes a single integer as its parameter. And again, I've not attempted to be fancy here. I could have parameterized on an arbitrary type, but I'm just making the leaves contain integers for simplicity. And I also have a node constructor, and the node constructor is going to take two subtrees as arguments. So to summarize, I've declared a new type of binary trees, and it's got two constructors, a leaf constructor which takes an integer parameter, or rather a single integer parameter, and then a node constructor which takes two subtrees as parameters. So nice, simple, recursive data type. So now we can think about defining a function which flattens such a tree. So the flatten function is simply going to take a tree. So it takes an argument of type tree, and it's going to flatten it down to give a list of all the integers which appear in the tree. So flatten takes a tree as an input and gives you a list of all the integer values which appear in the leaves. And this is a very straightforward function to define. So as you would expect, we have two cases. We can say what happens if you flatten a leaf which contains the value n. Oops, forgot the n here. And what happens if you flatten a node which has two subtrees, L and R. Okay, so let me just move this equals over a little bit. So what do we do in each of these two cases? Well, both of the cases are entirely straightforward. If we're flattening a leaf, all we're going to do is put the integer n into a singleton list on its own, and then we're done. And if we're flattening a node, all we're going to do is the obvious recursive thing. We're going to flatten the left subtree, and that will give us a list. And then we're going to flatten the right subtree recursively, and that will give us a list. And now we've got two lists, and then we can use the append operator to join these two lists together. So again, nice, straightforward, easy two-line definition for flattening a binary tree of this form. So this is a very natural definition. This is kind of the obvious definition which you'd write down for how to flatten one of these trees, but it's also inefficient due to the use of the append operator. And this time we're actually not going to calculate the precise complexity or time complexity of this function, but you could run some experiments and you'll find out that this is inefficient because of this use of the append. And actually it's doubly inefficient because we have two recursive calls to the flatten function. So the name of the game now is how can we eliminate the use of the append operator in the definition of the flatten function and hence make it more efficient. And what we're going to do is the same trick as last time. What we're going to do is first define a more general function that combines the behavior of flatten and append. So we're going to define a function that does a bit of flattening and a bit of appending. And this is exactly the same trick we used when we obtained a fast version of the reverse function. So let me write down an equational specification for the helper function, which we would like to define now. So I'm going to define a function called flatten prime, and it's going to take a tree t as its first parameter, and it's going to take a list of numbers n's as its second parameter. And what we'd like it to do is combine the behavior of flatten and append. So it's going to do a bit of flattening and a bit of appending. So in particular, what we're going to do this time is we're going to call flatten on the tree t. So we'll flatten the tree t, and then we're going to afterwards, we're going to append the list n's. Okay, so this is now our equational specification for what we would like the flatten prime function to do. Okay, so again, it's exactly the same trick as we used when we implemented reverse more efficiently. we formulated an equational specification, and it has an unknown. So the unknown this time around is the function called flatten prime, and this is the behavior which we would like it to have. We'd like it to behave as if it flattens the tree T and then appends the list ends afterwards, but we'd like to obtain a recursive definition which doesn't actually refer to the original flatten function or the original append function as well. So we're going to proceed by constructive induction, and in particular we're going to proceed by induction on the parameter T here. So as usual, we're going to begin with the base case for the calculation. So what we have to do this time is we're going to take our equational specification here and we're going to plug in T being a leaf. And then we're going to try and calculate in a systematic way what the definition of flatten prime should be for the case when T is actually a leaf. So this is very straightforward to do. So I'm trying to calculate what is flatten prime applied to a leaf n and some arbitrary list of numbers n's. And I'm just going to be doing a simple calculation here. So when you look at this, the only thing that I know about the flatten prime function is that it must satisfy this equational specification here. So on the left hand side, I've got flatten prime of leaf of n and n's, and what the specification tells me is that that had better be the same as flattening that leaf and then appending n's on the end. So if I simply use my specification at this point, and I won't write down the hints here, but they are important, and if I ask you this kind of thing in an exam, you need to write down the hints. But the hint here is I just apply the specification, and I'm going to get flatten of leaf of n plus plus n's. So all I've done is applied the equational specification for flatten prime. And now I can think, well, what can I do? Well, it's very clear what I do in this step. I know how to flatten a leaf, so I can just apply the definition of the flatten function. So the hint this time around would be applying flatten, and I'm simply going to get the value n sitting on a list on its own, and then I'm going to append n's on the end. And I'm nearly done at this point. It's very straightforward to see what we do now. If we just concatenate or append a singleton list onto a list n's, and we apply the definition of the plus plus operator, the append operator, that's simply going to give us back n colon n's. And at this point we're now done. We have the base case for the recursive definition for flatten. All we need to do is say that flatten prime of leaf of n of n's is simply going to be n colon n's. So let me just write the definition that we have calculated at the bottom of the screen here. So what we have calculated using the process of constructive induction is that flatten prime of leaf of n and n's is going to be n followed by n's. And this is exactly the definition which you would expect. Remember, what flatten prime does is it's going to flatten the tree which you give it and then append the list n's on at the end. So in this case, if we flatten this leaf, we're just going to get the single number n, and then we're appending the list n's on the end, so we just join it on using the cons operator. So entirely straightforward definition. It's exactly the one which we would expect. But again, the interesting thing is we didn't need to be clever and actually write this definition for ourselves. It arose systematically just by trying to solve this equational property for flatten prime in the base case. And this gives us the definition in the base case, essentially for free. So we can move on to the inductive case now, and it proceeds in precisely the same manner. So we're doing the inductive case. And again, we just start with the left-hand side of the equational property. So this time around, we have flatten prime, and we have a node with a left subtree L and a right subtree R, and we have a list of numbers n's. And again, we just go through the same kind of process, the same kind of equational reasoning we've been doing for a few classes now. We think, what's the natural thing to do? Well, again, starting from this point, the only thing we essentially know about the definition of flatten prime is that it must satisfy its equational specification. So if we apply that equational specification, what we would get is we would have flatten of the node LR, and then we would be appending ends on at the end. So we've simply applied the specification for the flatten prime function. Then we can think, well, what do we do now? Well, this time we can now once again apply the definition of flatten. We know how to flatten a node. That's entirely straightforward. So I can flatten the node, and that's simply you flatten the left subtree, and then you append flattening the right subtree, and then we just copy down everything else which we had. And notice that I've been careful with the brackets here, so when I expand out the definition of flatten here, I put brackets to the left with the append operator, just to make sure I'm getting things in the right order. So now we can think, what's the natural next step? And actually, the advice I gave you in the last class is when you see repeated uses of appends like this, then if they're bracketed one way and you're doing one of these kind of constructive induction calculations, it's almost always a good idea to apply associativity of append and re-bracket the other way. So this time around, we're bracketing to the left. Let's re-bracket to the right by exploiting the associativity of append. So exploiting that, I could get flatten L plus plus. And now I'm going to bracket to the right. So I'll get flatten of R plus plus ends. Okay, so now we think, what do we do? And this is the point, just like with the calculation for the reverse function, where we remember that we're doing an inductive calculation. So we're allowed to assume that our equational property in the red box here is true for the left subtree L and any old list ends, and it's also true for the right subtree R and any old list ends as well. And what we see is that we have this pattern appearing a couple of times in the term which we're manipulating. So we can actually apply our induction hypotheses at this point. So here is one of these terms. We have flatten of R plus plus ends. So by induction, we're allowed to assume that that's the same as flatten prime of R and ends. So if I rewrote that part, so I'll copy down what I had here, L plus plus. So by induction, the stuff in the brackets here is going to be the same as flatten prime of R and ends. So we've applied the induction hypotheses for R. Now we can do exactly the same for L. What we notice we have now is we've got flatten of L plus plus some list. And inductively, using the induction hypothesis for L, we're allowed to assume that that's the same as flatten prime of L and that list. So the induction hypothesis for L allows us to conclude that that's the same as flatten prime of L, and then in brackets we have flatten prime R ends. And again, at this point we are now done. If we take this equal that, this is now the recursive case for the definition of flatten prime. So let me just write this down at the bottom of the slide. So what we have in the end is we have calculated, using the process of constructive induction, just starting from the equational specification of flatten prime, that flatten prime of node LR, and then we have a list ends, is simply going to be flatten prime of L, and then in brackets we have flatten prime R and ends. And by construction, this recursive case here satisfies this equational property in the red box. So we know that flatten prime of t and n's is going to have the same behavior as simply flattening the tree and then appending the list on the end. And whereas the base case, maybe it's quite easy to write that without actually using the process of constructive induction, this time around, I think it's actually quite tricky, if you haven't seen it before, to work out how to actually define flatten prime in the node case. So this is where constructive induction is really helping us. We didn't need to know this definition in yellow. We essentially obtained it for free by applying this simple calculation process. Now that we've completed the calculation, we can wrap up this example by giving the full definition for the flatten prime function. So what we've done is we have obtained a function called flatten prime, and it takes two parameters. It first of all takes a tree, then it takes a list of integers, and it's going to combine those to give a list of integers. So that's the type of flatten prime. And then we calculated the two cases for the definition. So flatten prime of a leaf, n, and some numbers n's, that was something. And then we had flatten prime of a node with a left subtree L and a right subtree R, followed by some list of numbers n's. And in the two cases, in the base case, we simply returned n colon n's, and in the recursive case, this was the kind of non-obvious one where constructive induction really helped us. We wrote flatten prime of L, and then flatten prime of R, and then n's. And that's the complete two-line definition for the function. But of course, it's not really the flatten prime function that we're interested in. We're interested in obtaining a more efficient version of the original flatten function for trees. And just as with the reverse example, this is very straightforward to do. We can recover an efficient version of this function. So all we need to do is I'm going to define a new version of flatten, and it's got the same type as the original function. Takes a tree as an input, and it's going to flatten it down to give a list of all the integer leaves that it contains. And we're going to define this simply by calling flatten prime. So you give flatten a tree t, and we're going to call flatten prime. And remember, flatten prime takes two parameters. It takes a tree as an input, and then a list of numbers which you want to append on the end. So obviously what we're going to do is we're going to pass in the tree t, and then we're going to pass in the empty list here as our initial accumulator value. And this definition has the same behavior as the original flatten function. So what's actually going on here on the right hand side? If you look, why is passing in the empty list the right thing to do? Well, you can look back again to the specification for what flatten prime does. It takes a tree t and a list of numbers n's, and then on the right hand side it's going to flatten the tree and then append the list of numbers on the end. So if we provide the empty list as the list of numbers, on the right hand side here, this flatten prime function is going to simply append the empty list on the end, which of course is actually going to do nothing. So that's why supplying the empty list as the parameter here is the right thing to do. So this is our final version of the flatten function now, and I think you'd agree it's less clear than the original definition. In particular, this recursive case is something you maybe need to think a little bit about why it's actually correct. But in principle, you don't actually even need to think about it because we obtained it calculationally by the process of constructive induction. And again, the main point here is that this function is less clear, but it's much more efficient. And again, you could try some simple examples of this in the GHC system and find that it's actually hugely more efficient than the original function which we wrote. And once again, it's written in this so-called accumulator style, we're passing in an additional list here, which is going to be used to accumulate the result of flattening the tree. And once you get used to it, this kind of accumulator style of programming is actually quite natural, and it leads to highly efficient programs as we see here. So what we're going to be doing for the rest of today's class is starting off our final case study for the course. And what we're going to be doing is considering the problem of proving a simple compiler to be correct. And remember, what a compiler does is it takes a program in some high-level language and then translates it down to an equivalent program in a lower-level language. So what we're going to be doing today is actually setting up the basic problem that we're going to be trying to solve. So we'll kick things off by, first of all, defining what is the source language for our compiler. I'm going to keep this very simple because I want the focus to be on actually thinking what does it mean for the compiler to be correct rather than compiling a realistic language. So the source language I'm going to consider is just a simple data type of arithmetic expressions, and we'll keep this as simple as we could possibly make it. We're going to say that an expression is either going to be a value which has an integer parameter, or it's going to be the addition of two sub-expressions. Okay, so the language for our compiler is going to take an expression as input, and an expression is either going to be an integer value or the addition of two sub-expressions. So the kind of things we'll be compiling is things like 2 plus 3 plus 4. So very, very simple. Then we're going to be thinking about the correctness of a compiler for this language. So we need to think, what do programs or what do expressions in this language actually mean? So we're going to consider a semantics or meaning for these kind of simple expressions. And you can think, well, what does an arithmetic expression like 2 plus 3 plus 4 actually mean? Well, you can think of it as meaning whatever value you get by evaluating that expression. So we're going to give semantics to expressions by having a very simple evaluation function. And it's simply going to take an expression as input, and it's going to fully evaluate it and give whatever the appropriate integer result should be. And of course, this is extremely easy to write. It's just a 2-line simple recursive definition. So I can write down the skeleton first. So if we evaluate a value, we get something. And if we evaluate the addition of two sub-expressions x and y, we're going to get something. And obviously in the base case, it's very simple. We just return the underlying integer n. And in the recursive case, we're simply going to evaluate the first thing, and then we're going to add that on to the result of evaluating the second thing. So just to summarize what we've got so far, we have our source language, which is simple arithmetic expressions built up from integers using an addition operator. And the semantics or meaning of this language is given by a simple evaluation function, which just takes an expression as input and then gives you its corresponding final integer value. So now that we know what the source language for the compiler is, we can move over and think about the target language. And this is going to be given by a simple virtual machine. And the virtual machine is going to have 3 simple components. So the first of the component is going to be a stack. It's going to be a stack machine. So I'm going to declare a type for stacks. And a stack is simply going to be a list of integer values. And the idea is that the first number in the list is going to be like the top of a stack. So remember, a stack is like a stack of books. You always add values to the top of the stack and you remove values from the top of the stack as well. So a stack is simply a list of integers where the first thing in the list is the top of the stack. Our machine is also going to have a code component, And the code is simply going to be a list of basic operations that operate on the stack. So code is simply a list of operations. And then the final component of the machine, we're going to have a data type for operations. And these will operate on the stack. And it turns out for this simple source language that comprises integers and addition, all we're going to need is two basic operations. So we're going to need an operation called push, and it takes an integer parameter. And the idea is that this simply pushes a given integer on to the top of the stack. So if your stack contained the values 2, 3, 4, and then you pushed a 1 onto the stack, then your stack would contain the values 1, 2, 3, 4. Puts that new value on to the top of the stack. And then we need one more operation. We need an operation called add, and it doesn't take any parameters, but what it will do is it will take the current stack, remove the top two values from the stack, add them together, and put their sum back onto the stack. So for example, if the top two values on your stack were 1 and 2, and you performed an add operation, you would remove the 1 and the 2, add them together to give 3, and then you'd put the 3 on to the top of the stack. So again, just to summarize, this is the target language for our compiler. It's a simple virtual machine which comprises a stack and code, where code is a list of operations. So just as we gave a semantics to the source language, so we can also give a semantics to our target language or virtual machine. So in order to do this, we're going to define a little function called exec for execute. And what exec is going to do is it's going to take some code, which is a list of operations. It's going to take a stack, which is the initial stack for execution. And then it's going to execute that code given that stack, and then it's going to give us back a final stack. So we can define this by recursion, depending on the structure of the code. So let me write down the base case for this. So if you execute code which has nothing in it, in the context of a given stack, then we're going to do something. And I'll leave space for filling this in a moment. The second case is if you execute a push operation. So we're pushing the value in, and then we have some more code following on, which we then need to remember to execute. And you have a given stack S, then you're going to do something. And then the final case for the execution function is if you're executing and the first operation in the code is an add operation, followed by some more code. And this time we need to be a bit careful. We need to match on the stack. So we need two values on top of the stack, say M and N. And then you have the remaining stack S, and then we will decide what to do. So again, we have our skeleton here. You could be executing nothing, or you could be executing a push operation followed by some code, or you could be executing an add operation followed by some code. So all we need to do now is fill in the right-hand side of this definition for each case. So in the base case, it's very straightforward. If you give me no code and you give me a stack, then there's nothing to do. I will simply return that same stack. In the second case, if the first operation is a push and C is the code that you need to execute afterwards, and S is your initial stack, then this is very simple. All we're going to do is we're going to execute the remaining code C, but we will take a different stack. We will put the value N, which we want to push. So we want to push N onto the stack. So we'll put it onto the stack that we already had, and then we'll call the execution function with this new stack. So again, very simple. And then in the final case, we have matched on the top two values on the stack, and we want to add them together. So this is also very simple. We're simply going to execute the remaining code C, and we'll add the two values N and M together, put them on the top of the stack, and that's us done. Okay, so this is the semantics for code we simply take a stack as an input and we transform it using the operations in the code to give a final stack. So now we can define the final piece of the jigsaw puzzle, which is the actual compiler itself. And remember, a compiler translates from a high-level language down to a low-level language. And in this case, the high-level language is arithmetic expressions, and the low-level language is code for our simple stack machine. So what our compiler is going to do is it's a function, let's call it comp for compile. It's going to take an expression as input, and it's going to translate it down into equivalent code for our simple virtual machine, which operates by means of a stack. So how do we define the compiler? So we're going to define it by pattern matching on the expression. So we could have a value, or we could have the addition of two sub-expressions x and y. So all we need to do is think, what do we do in each of these two cases? And both of them are straightforward. In the base case, how do we compile a value? Well, all we're going to do is we're going to push that value onto the stack. But remember that code is a list of operations, so we need to put that into a little list on its own. So if we want to compile a value, all we do is emit a single operation which pushes that value onto the stack. Very straightforward. Then we can think, how do we compile an addition? Well, what we're going to do this time is we will compile the code for, or we'll compile the first expression x, then we're going to have an append, and then we will compile the second expression y, and then finally we're going to produce an add operation at the end. So this is the recursive definition for how you compile an addition. So how is this actually working? Well, if you think, what is this going to do? So this is going to emit code which will leave the value of x on top of the stack. And then this is going to produce code which will leave the value of y on top of the stack. So now you will have two values on top of the stack, the value of the expression x and the value of the expression y, and then finally you can add them together using the add operation. Okay, so a nice simple two-line definition for how you can compile an expression. And note that it uses the append operator here. So this is something we're going to come back to later on, in fact, in the next lecture. So before we move on now to thinking about what it means for the compiler which we have written to be correct, I just want to do a simple example to make sure that everyone's comfortable with these basic definitions and what they are actually doing. So what I'll do now is imagine we had typed in all these definitions and we start up GHCI and we get the little greater than prompt. And what I'm going to do first of all is I'm going to define an example expression E. And the way I'm going to do it is I'm going to make it an addition, and the first parameter of the addition is also going to be an addition. It's going to be the addition of the value 2 to the value 3. And then the second parameter of the addition is simply going to be another value. It's the value 4. So it's a bit verbose what I've had to write in here because I'm using the add and the val constructors, but this is essentially just 2 plus 3 plus 4 written in our internal notation for expressions. So if I had an expression like this, what could I do with it? Well, the first thing I could do is I could apply my evaluation function to it. And if you evaluate 2 plus 3 plus 4 in this internal representation for expressions, obviously you're just going to get back exactly what you expect, which is the value 9. But evaluation is not the only function I have to process an expression. I could also compile the expression. So I could call the compiler on the expression E, and this will give me a sequence of operations. It will give me some code. And the operations it will give me a push of 2, and then a push of 3, and then an add. And that is the result of compiling the first sub-expression here. So we've got 2 plus 3. And the way this is compiled is you push the value 2 onto the stack, then you push the value 3, then you perform an addition which will remove those 2 values and push the value 5 onto the stack. And then the remaining operations which you'll have here, you will have a push of 4, and that simply corresponds to the second argument of the outer add here. And then finally you'll have a top level add, which is going to add together the result of the 2 sub-expressions. So this code will add together 2 and 3. This will put the number 4 onto the stack, and then this will add the 5 and the 4 to give 9. Okay, so exactly what we'd expect as the output of the compiler. And then we can think about how do we actually run this code? Well, we could use our execution function. So we could imagine executing the result of compiling that expression E. So comp of E will give us exactly all of this code here. If we run all of that code, or we execute that code using an empty initial stack, what we're going to get back is a stack which just contains the final result value 9. So what we have on the slide here is an illustration of all of the functions which we have defined. So now we can think, what does it actually mean for our compiler to be correct with respect to the semantics? And this is very easy to see. When we took our example and we evaluated it, we got the result 9. And correspondingly, when we took our example and compiled it and then executed the resulting code using an empty initial stack, we also got the result value 9, but this time sitting in a little stack. So this example gives us the key to formulating what it means for our compiler to be correct. So we can write down a simple statement of compiler correctness now. So compiler correctness. So what does this actually mean? So what it means for our compiler to be correct is if we execute the result of compiling any old expression E using an empty initial stack, then what we expect to get back is the evaluated value of that expression sitting on a little stack on its own. And this is exactly what we saw with our example. When we compiled our example expression and we executed it using an empty initial stack, we got the value 9 sitting in a little stack on its own. Okay, so this is just generalizing from this particular example we had here, where we were taking this particular expression and we evaluated it and we get 9, and then when we compile it and execute it, we also get 9 sitting on a little stack. All we're doing here is generalizing from this particular example, and we get this compiler correctness property here. If you try and prove this, however, you'll come into a problem. And the problem is that in order to prove this by induction, it's actually a problem that you have the empty list or the empty stack sitting here. And actually, it's a good exercise to try this yourself. Try and prove this property using induction, and you'll find that you get stuck because we have the empty list sitting here. And this is a common thing that you find when you're doing inductive proofs. If you have specific values, such as the empty list or empty stack sitting here, often you need to generalize these for the purposes of proof. So what I'm actually going to do here on the left-hand side is I'm going to replace that empty stack by an arbitrary initial stack. So I'm generalizing from the empty stack to an arbitrary initial stack. And then I need to think, well, how can I modify the right-hand side in the corresponding way? And this is also very simple to do. All I'm going to do is I'll rub out the brackets here. Try and do this carefully. And all I'm going to do on the right-hand side is put the value of the expression E maybe put some brackets in here to make it precise, put the value of the expression e on top of the stack. So this is our final compiler correctness statement. Let me just read it in words. What it is saying is if you take any old expression e and you compile it, so that will give you some code, and then if you execute the resulting code using an arbitrary initial stack, what you will get back on the right hand side is the same stack but with one extra value sitting on top of the stack, and that is the value of the expression itself. Okay, so this is our final compiler correctness theorem, or compiler correctness equation. So to wrap things up today, what I'd like to show you is how we can also formulate this compiler correctness result in pictorial form. And this turns out to be very simple to do, but it also has some benefits as well. So what we're going to be doing is forming a square, and at the top left side of the square we're going to be taking an expression. And what could we do with an expression? Well, one thing we could do with an expression is simply evaluate it. And if we evaluate an expression, we're going to get an integer value. So if we evaluated 2 plus 3 plus 4, we're going to get the integer 9. Something else we could do with an expression is we could go down here and we could compile the expression. And if we compile an expression, of course, we're going to get back some code. So we've got two ways of processing an expression. We could either evaluate it to give an integer, or we could compile it to give some code. So I've got two sides of a square now. How am I going to complete the whole square? Well, what I'm going to do is in the bottom corner, I'm going to write a stack. And then I'm going to draw two more arrows, and then we're going to figure out what could we write on these two arrows to correspond to this compiler correctness equation. Well, let me do the downwards arrow first. What I'm going to do here is write :s here. And this is a bit of Haskell notation here. This is called a section. And what this is going to do is take any integer and then put that integer on the start of the list s. So in particular, s is going to be a stack. So this is going to put whatever integer we obtained up here onto the stack s. So you can imagine now following around the right-hand path. If we take an expression and then we evaluate that expression, we will get a number, and then we can put that number onto the start of the stack s, and that will give us a final stack. So that's one way round the square. How do we complete the bottom of the square? Well, I'll use again some special Haskell syntax. I'm going to write exec of s here. And what this is going to do is you give some code, and then what this is going to do is you're going to execute that code using the given stack s, and then you'll get back a final stack. So now you can imagine following around the left-hand path in this square, and what this is saying is you take an expression and you compile it and you get back some code. And then what you're going to do is you're going to execute that code in the given stack s, and that will give you back a final stack. And what this square is called is what's called a commuting square. And I like to write a smiley face in the middle to show that the square commutes. And what it means for a square to commute is that both of the two paths always give the same end result. So what does this mean for us? Well, what it means is if you take an expression and you evaluate it to get an integer, and then you put that integer on to the stack s to give a final stack, then that should give the same result as compiling the expression to give some code and then executing that code in the initial stack s. So for this square to commute means that these two paths, one going round this way and the other one going round this way, should always give the same result. So what this gives you is a nice pictorial way, removed part of the face. It gives you a nice pictorial way of understanding this compiler correctness equation. It says if you compile an expression and then execute the resulting code using a stack, you get the same result as evaluating the expression and then putting it on to the stack. So it's exactly the same thing, but written in pictorial form. And one of the advantages of the picture here is that the types become clear. So you see very explicitly the 4 types sitting here. So that's basically it for today. What we're going to do in the next class is think, how do you actually prove this property correct? So what we've done today is we've set up the problem, we've defined all the component functions, we've formulated the compiler correctness theorem. What we'll do in the final lecture of the course is we'll think, how do you actually prove this correctness equation? So that's it for today. I will see you again in the last lecture next time.